So, good evening, everyone. Myself, Chaitra Borkar, a Ph.D. scholar from IIT Delhi, and I welcome you all to the 12th and the final live session for the for the NPTEL online course Basic Principles and Calculations in Chemical Engineering. Um, this course has been instructed by Professor S.K. Majumder from IIT Guwahati. So, let's get started. Some general information about these live sessions is that these have been conducted every week on Tuesday from 7 to 9 p.m. for the duration of this course. This is the last week of this course. There will be one more extra session just to clarify your doubts tomorrow at the same time. And the recordings of these live sessions have been made available to you through my through the link shared with you, as well as you can access it through my YouTube channel. The structure of the sessions has been that we'll first go through the overview of the lectures for the corresponding week, and then solve some sample problems related to your assignment for that week. So we'll go through the overview of lecture 34 and 35, which are the basically the final lectures of this course. So it was about the case study of a whole plant for the cumin production as well as the phenol production. So we start with the cumin production. So the main reaction that leads to cumin is that cumin can also be called as isopropyl benzene. So cumin is isopropyl benzene. So the main reaction is between benzene and propylene. This is propylene. Okay, or you can say propene. And this is benzene. And this is what you get to mean. This is your main product. Another side reaction also takes place in this case, which is you get cumin from the above reaction, and again propylene may react with it. Uh, so that's why you get diisopropyl benzene. Di means two isopropyl group is there. So, and this is in para position. It can also be in meta position. So, what is meta position? Suppose this is isopropyl group. The another isopropyl will be here. Okay, so this is meta, but majority only para diisopropyl benzene is formed. So this is called DIPB. And the reaction temperature and pressure is 350 degrees Celsius and 25 atmosphere. So very high temperature, moderately high temperature and very high pressures. So it is a gas phase reaction. All the reactants are in gas phase, but happens over a catalyst. So basically a heterogeneous catalytic reaction. So it can happen either in shell and tube reactor or a packed bed reactor. Or you can also write this as tubular reactor. And the reactants are sent through the tube side, and in these tubes the catalyst is packed. The catalyst can be the zeolite based catalyst or the solid phosphoric acid. So this is the flow sheet for your cumin production. um, I will not go through the mass balance and the energy balance taken up in the lecture, as it is quite straightforward and it's quite elaborate. I'll go through whatever the processes are involved in this cumin production and phenol production, and then we'll solve some sample problems. So basically, this is the storage for benzene, and this is storage for propylene. So it goes to the feed vessel, and from there it goes to the vaporizer. This is the benzene. This is the benzene vaporizer, and from storage of propylene goes to the propylene vaporizer. You just focus on these forward going lines right now. So from vaporizer, benzene is vaporized at 243 degrees Celsius. And from here, it is mixed and then sent to the furnace. And from there, it goes to the tubular reactor where catalyst is there. So here the reaction takes place, and the reactor effluent from here, it goes firstly to, basically there is a heat exchange going on here. So this stream, which is it's basically heating up this benzene. So you are actually using this heat. So why there is heat in this is because it's an exothermic reaction, and to maintain the temperature, uh, exothermic reaction, to maintain isothermic condition, isothermal condition. Kindly mute yourself. Excuse me. Kindly mute yourself. Hi, Vinod, can you mute yourself? Yeah, thank you. So this is an exothermic reaction that is taking place in this tubular reactor, and to maintain the isothermal condition, basically because it's an exothermic reaction, so it will release heat. So it is basically generating heat. So to maintain the isothermal condition, you have to basically remove that heat. So how do you remove that? It's through pressured water. So through the jackets, through the shell side, the pressured water is being circulated so as the heat is removed. So this reaction effluent, it also has some heat. So that heat is utilized basically, suppose this is a heat exchanger, to vaporize this benzene. Then it again goes to vaporize the propylene as well. This heat is also being utilized, then heated and then cooled. So then cooled, and here this valve is there which reduces this pressure control valve, which reduces the pressure. So it has 25 atm pressure here, but it reduced to just above atmospheric pressure, and this is the separator. So your reaction effluent will be basically, there may be some benzene, there may be some propylene, and this propylene, it's not pure propylene from the storage, it is propylene plus propane. So propane is just there; it does not react. There is no reaction going taking place. So there will be some propane as well, and there will be cumene because the reaction has taken place, and there it will be DIPV. So this separator basically separate into two streams. So this upper stream is basically propane and propylene gaseous, and it is used as a fuel in the furnace. And whatever the remaining are, it will be DIPV, cumene, and benzene, sorry. So this is basically, I'll write B, C, and D. So this is benzene, this is cumene, this is diisopropyl benzene, DIPB, in this stream. And then it is preheated, uh, then sent to the benzene column or the distillation column. This is called benzene column. So because it separates benzene from the rest of the reaction effluent mixture. So you get around 98.1% benzene from here, and the rest is then sent to the cumene column. So and the rest will be basically cumene and DIPB. So here this is the cumene column, another distillation column. So from here you get around 99.9% cumene in the top product, and the bottom product is DIPB, which is then used to preheat this mixture going into the benzene column. So that is how you get the cumene production. Another case study was about phenol production. So there are majorly four steps involved. So first step is basically you react the benzene. So what is phenol is? This is your benzene or the phenyl group, and above that is OH. This is your phenol. I can make it a bit better. So this is your OH group. So this is your phenol compound. So basically there are four steps. I can first step is basically react the phenol with the fuming H2SO4, and this is the reversible reaction which gives us benzoyl sulfonic acid plus water. So because this is reversible reaction, so as to force it towards the forward direction, you keep on removing water. Um, and because it also generates heat, you can also remove the heat. Because this is a reversible reaction, so if you dilute this benzene sulfonic acid and uh, add heat, this will go towards the reverse direction. You don't want that. That's why you keep on removing the water as well as removing heat. So this is the first reaction, or the first step. It is called sulfonation. Then the next step is basically benzene sulfonic acid, or abbreviated as BSA, plus this sodium sulfite. This is sodium sulfite, which gives us, basically it's a neutralization reaction, because you have some acid, you have some salt which can neutralize it. So it is called neutralization. So sodium benzene sulfonate is formed. This is suppose an uh, ester of sulfonic acid. So we get neutralization. Now this sodium benzene sulfonate, or SBS, is reacted with sodium hydroxide, or fused with sodium hydroxide to give us sodium phenoxide. So this step is called as fusion, and it is one of the it takes quite a long time. It has 5 to 6 hours residence time. Um, so we get sodium phenoxide, which can be, the structure of that is ONA. Okay, and then this sodium phenoxide, or SP, is then acid. Then the acidification takes place, where so it reacts with H2S4 to give us uh, crude phenol plus Na2SO3. So this is again acidification to give us crude phenol, which is then vacuum distilled to get the uh, pure phenol form. And this is a large scale batch cycle operation. 5 to 6 hours are required for the fusion process, as I told you. So here the flow sheet is shown. Sorry. So here you can see that sorry. So here you can see in this flow sheet that firstly this is the benzene. It goes through the evaporator to the sulfonator, and in the sulfonator the H2SO4 is added. The sulfonation takes place here. Then from there, whatever the reaction effluent are, it is taken to the neutralizer, and the Na2SO3 is added. So Na2SO3 neutralizes it to sodium benzene sulfonate, and then from there uh, from the neutralizer it goes to the fusion pot, and already the fusion material, or you can say NaOH, is already present here, and it forms the sodium phenoxide, and from there it goes to the settler, uh, and from there again filtration, and then from there it goes to acidifier. The acidification takes place, and then from there you go to the vacuum still or vacuum distillation column, where you get the from here it is crude phenol. You get the finer form of or the pure form of phenol from here, and the steam still is there, so as to whatever the crude phenol will be on the upper part, and whatever the lower part is, it it will have salts as well as some form of phenol. So steam stripping is done so as to get more phenol from there, and whatever the salts are, they are taken to the centrifugator and the filtration units, so as to recover the Na2SO3. So this is a little bit easier to understand flow sheet. So here you can see again just a repetition of the previous slide. We have benzene. It goes to the sulfonator. We also have H2SO4 which comes in. So then from the sulfonator, the sodium benzene sulfonate, sorry, the benzene sulfonic acid is taken to the neutralizer where we add Na2SO3 so as to get sodium benzene sulfonate. From there, the filtration is done and it goes to the fusionator. In the fusionator, we add the NaOH to get the sodium phenoxide, and from and from here it goes to the acidifier. Here you add H2SO4 so as to acidify the sodium phenoxide so as to get the crude phenol, and the crude phenol from the top layer is taken to the vacuum distillation column. This is the vacuum, so as to get your fine or the purer form of phenol, and the bottom part of this acidifier is taken to the steam stripper so as to recover phenol, as well as so you see from this top part it is again going into the vacuum distillation. So this is basically your phenol from the steam stripper, and whatever the salts are, it is then taken to the centrifugal crystallizer and the centrifugation so as to recover this Na2SO3. So in these two case studies, you have seen how you basically in not just the phenol and cumene production, you see how the streams are various streams are used for the heat exchange. You can make it energy efficient. So whatever the heat is being generated, you can use that heat itself or the extra heat itself so as to heat other streams as well which require heating, or how you can recover the extra product as well. So mostly the process, if a process is self-sufficient itself, it doesn't require any extra energy from whatever is required. Suppose just the heating requirements for the reactor itself, and not any other heating requirement. You can say it is quite self-sufficient. The percentage of self-sufficiency is quite high in that. So we then now move on to the sample problems related to your assignment 12. So the first question is, which of the following units are not present in human production? A, tubular reactor, B, fusionator, C, distillation column, or D, furnace. So what is the correct answer here? Which is not present? These units are not present in human production. What will be the correct answer here? Can anybody tell me the correct answer? So we have a tubular reactor in our cumene production. We have a distillation column. We saw it's a benzene column or the cumene column. We do have a furnace as well. What we don't have is a fusionator, which is in phenol production. So the correct answer here is the unit that is not present in cumene production is the option fusionator. Next question, how many moles of propylene are required to make 1 mole of DIPB? Considering the cumene production as the main reaction and DIPB production as the side reaction. So there is a reaction system. I will say benzene, and then propylene. This is C, this is C. It will be already 2 bonds to CH2. This already has 3 bonds to CH, and this is CH3. So this is benzene plus propylene. It gives us isopropyl benzene. So already 3 bonds to CH, CH3, and CH. Okay. So this is isopropyl benzene or cumene. Now This is the main reaction. What is the side reaction is? Then this cumene plus propylene again. It gives us diisopropyl benzene. So CCC, CH3, then again CH, CH3, and CH3. So this is your DIPB. So if this is the main reaction and this is the side reaction, so in this system, you basically require to make DIPB, you require two propylene atoms, because firstly this propylene would react with benzene to give us cumene, and then this cumene is again reacted with propylene to get DIPB. So you basically require two propylene atoms, or sorry, two propylene molecules or moles. So in abbreviation, we can write B as benzene, propylene is P, it gives us cumene. Then again, this cumene plus propylene gives us D or diisopropyl benzene. So you require 2 moles of propylene. So this is the correct answer. The reaction condition for cumene production is 350 degrees Celsius temperature and 4 atmospheric pressure. Is this statement true or false? So we have discussed this before, that the reaction condition is 350 degrees Celsius temperature and 25 atm pressure. So this is a false statement. Now you have given a figure from the flow sheet of cumene production. So what is getting separated here? What are these two streams? What material from these two streams, you can say, is flowing? So there is some feed, and basically this is from the reactor itself. So this will have propylene plus propane, I abbreviated as PR. Then we have unreacted benzene. We have this is also unreacted propylene. We have cumene formed and then DIPB formed. So this is what the feed is in the separator. So from the top part we saw from the flow sheet itself that the top part is propylene plus propane, which is then used as a fuel in the furnace. And then this is the rest, benzene plus diisopropyl benzene plus cumene. So that is what is being separated. Okay. What is the top product from this column? So you saw this is the feed preheater. So before this is the separator. And after this is another distillation column. And this is another distillation column in the middle. So here, what is the top product? So we saw that from the separator, whatever is going in the distillation column is basically B, D plus C, or benzene, diisopropyl benzene, and cumene. So the top product here is benzene itself. So we get benzene, which is then again sent to the uh, feeder tank of the benzene. So we get around 98.1% benzene here. Okay. And again, the bottom product will be whatever is the remaining, diisopropyl benzene plus cumene. Next question, either dash or dash catalyst can be used for cumene production. So what will be the correct answer here? MnO2 and xyloid based. We know zeolite based is there. Solid phosphoric acid and MnO2. We know solid phosphoric acid is there, but MnO2 is not known. HGO and MnO2, I don't think so. The last option is correct. Solid phosphoric acid and zeolite based. Next question, the 99% conversion for cumin production is based on. So in your flow sheet, we saw there is cumin production and the basis is 99 conversion of what reactant? So it is propane, benzene, propene or propine. So it is propene. Or another name for this is propylene. So this is C3H6 and this is C triple bond C. So it will have already triple bond, all bond satisfied, and this is, so it will be C3H4. Okay, and this is C3H6. I can also show the structure here. CH3, CH, double bond, CH2. So this is C3H6. It is propylene is also known as propene. Basically, this is the actual name propene, which is usually used, and this is the trivial name propylene, another name for propene. Okay, 99 conversion of propylene is the basis for cumin production. Next question, steam is used to maintain temperature of the tubular reactor for cumin production. Is this answer correct? I mean, this statement true or false? So we saw that tubular reactor, in the tubular reactor, the reaction is exothermic. Already the temperature is, at 350 degrees Celsius, whatever the reactants are coming into, they are at 350 degrees Celsius and 25 atmospheric. So this is an exothermic reaction itself, whatever the reaction is going on in the tubular reactor. So as to maintain that temperature at this temperature, so if heat is being added into the system, basically it is releasing heat. So to maintain this 350 degrees Celsius, we will have to remove the heat. Remove heat. So as to remove heat, you don't use steam. You used cooling water or pressurized water. So this is a false statement. You need a cooling media, not a heating media. So next question, what is the top product of the second distillation column in cumin production? What is the top product of the second distillation column in cumin production? So we saw in the bottom part of the flow sheet, there is a separator. There is a first distillation column and the second distillation column. So whatever the bottoms is going into this. The top is going up, and this is the top product, and this is the bottom product. Just a rough, uh, rough representation. There are no reboilers or condensers here. So this is distillation column 1, this is distillation column 2, this is a separator. So you saw that the separated part is B plus D plus C. It goes into this first column, you remove B or benzene. Then D plus C goes into this second column. So C is the top product and D is the bottom product. You have a logic for that as well. Why benzene is in the top part of this first distillation column and why cumin is the top cut of the uh, second distillation column? It's because of their, if you see, molecular weight as well. So in the organic compounds, higher the molecular weight, higher will be the boiling point. So if the boiling point is higher, it will be less volatile. So whatever the less volatile compound is there, it will be from the bottom. Whatever is the more volatile, it will come out from the top stream. So benzene is C6H6, and then uh, you add another propyl. So propyl group to benzene, it gives us cumene. So C6H5, another. Um, I can just make this. So this is C6H5. This is C, again H only, CH3 and CH3. So C6H5, C6H6, C6H12. So C9H12 basically. C9H12. And then DIPB will be again C6H4 plus these C6, and then again these you can say again this is, wait a minute, so C6H14. So 14, this is sorry, this is 18 and C12H18. So the higher the molecular weight, so this will have a lower molecular weight than this, and this will have a lower molecular weight than this. So this is least volatile out of these three. So it will be the top product for the first distillation column. This is the mid volatile. So this will be the top product of the second column. This is cumene. This is DIPB. I can just confirm once the molecular the formula for DIPB if just once. So this is C, C, and C. This is again C and C and C. So you have C6 and again six more C. So C12 is correct. And then H, 4H from here. And then H3, H, H3, H3, H, and H3. So 7 and again 7. So 14H. So it will be, yeah, C12H18. Yeah, correct. And for cumene, so we have C6H5, C6, and again plus C3, so C9, and you have H5 already from this benzene ring, and these are 7, H7, so H12 only, so C9, H12. Yeah, correct. So more volatile out of these three will go from the top product in the first column. Then out of D plus C, whatever is the more volatile will be from the top product. So cumene. Heavier the molecule, higher is the boiling point, you can say. Next question. Cumene is used to preheat the benzene column feed. So you saw there is a separator. From there, there is a preheater in between, and from there it goes to the distillation column 1, and then whatever the bottoms are, it goes to the distillation column 2, and this is the top cut, this is the bottom cut. So it is saying that cumene is used to preheat the benzene column feed. This is a false statement because whatever the cumene is coming, it is coming from the top product. It is basically a condensed form. So it will basically be at a lower temperature. So and whatever the DIPB is coming out from here, it is going through a reboiler itself. So this is used to preheat the benzene column feed. So this is a false statement. So next question, the separator feed is cooled before entering the separator. Is this a true or false statement? So you saw in the flow sheet, this is a separator. Some feed is coming in, so it will have propane plus propyl. This is propylene. This is propane. We will have benzene. We will have DIPB, and we will have our main product cumene. So it is basically cooled before going to this separator or the flash separator as mentioned in the lecture. So it is cooled. So this is a true statement. We can confirm it from the flow sheet itself. So you see here, there's a cooler involved. So yeah, it cools your whatever the reactor effluent is before going to the separator. Next question. How many kilomole per hour is equal to 100 TPD of cumene? So I have not done the material balance formulas or material balance. I have not discussed that, but this is quite a straightforward question. So you have 100 ton per day of cumene, you have to convert it to kilomole per hour. So 100 ton per day of cumene you have. This is basically the basis of your plant, or you can say you need this much of ton per day cumene. So how many kilomole per hour will be there? How much will it be in kilomole per hour? So a day has 24 hours, and tons is again 100 into 10 to power 3 kg. So we know 100 into 10 to power 3 kg upon 24 hours. So that will be the mass per hour. So molar flow rate, you can say. But you want mole. So you need to divide that again by the molecular weight, which is given to us 120.19. Or we can calculate it again. Cumene is C9H12. So 9 into 12 plus 12. It comes out to be 120 itself. Yeah. This is an accurate form 120.19. So basically 100 into 10 to power 3 into 24 into 120.19. You get this as, so this comes out to be 34.67 kilomole per hour. Okay. Next question. The fusionator has a very low residence time. This is a true statement or a false statement? So we saw in the overview of the lecture that the fusionator, it gives us sodium phenoxide. Okay, and we have sodium benzene sulfonate, and we add NaOH. So it is basically a very high residence time because it takes around 5 to 6 hours. So because of this system, this process itself, it is the phenol production from the benzene and the reaction with the H2SO4 is a large scale batch reaction itself. But we keep on removing the sodium phenoxide at regular intervals so as to keep the process in continuous form. So has a higher residence time. So this is a false statement. Uh, Next question, dash is used to get phenol from crude phenol. So we saw in the flow sheet itself, from the acidifier, the crude phenol is formed here. And the top cut is basically this crude phenol is taken into the distillation column, which operates at vacuum. So from here we get a purer form of phenol, vacuum distillation. Next question, sodium phenoxide is, first option is NaOC6H5, NaOC6H6 is the second option, third option is Na2OC6H5, and the fourth option is Na2OC6H6. So we saw or discussed earlier that sodium phenoxide is, right, this is, so this is C, 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 C and C. So C6 is correct. It will have one H, 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 but this will not have an H because ON is attached to it. So C6H5ONA. So the correct answer is the A option. Or you can write it in another form is NaOC6H5. Cumene is also called methyl benzene, isopropyl benzene, ethyl benzene, or propyl benzene. So if you see, methyl benzene is basically CH3 and benzene. So no, this was not cumene. If you go for ethyl benzene, this is CH2, CH3, a phenyl group attached. Propyl benzene is again CH2, CH2, CH3. So this has three C's, but the it is attached to the end of this propyl group and not the middle. Cumene is basically CH, CH3, and CH3. So this is the isopropyl group, and this is our cumene. So correct answer is isopropyl benzene. Next question. Sodium benzene sulfonate is produced as the main product after fusion process. Is this a true or false statement? So we saw basically benzene plus sulfuric acid, or you can write HS in this. It gives us benzene sulfonic acid. Okay, this is fuming sulfuric acid. So H2SO4 plus SO3 basically. So it gives us benzene sulfonic acid. Then benzene sulfonic acid plus Na2SO3. This is the neutralization. It gives us sodium benzene sulfonate. Then this sodium benzene sulfonate, this is the neutralization. Sodium benzene sulfonate, then again fused with NaOH to gives us sodium phenoxide. Then sodium phenoxide plus again H2SO4 gives us your crude phenol. Okay, so you saw this is the fusion step, or whatever reaction takes place in a fusionator. So the main product is not sodium benzene sulfonate. The main product is sodium phenoxide. So this is a false statement. Next question, dash is formed after neutralization process. So we discussed just in the previous slide that neutralization process is basically benzene sulfonic acid plus Na2SO3, which gives us sodium benzene sulfonate. Okay, so this is the correct answer here. Please don't get confused between sodium benzoate and sodium benzene sulfonate. Sodium benzoate is basically, it is the carboxylic acid salt. Okay, and this is benzene sulfonate is sulfonic acid salt. These both are esters, but they are from a different acid itself. So this is from carboxylic acid, and this is from benzene sulfonic acid or benzoic acid, you can say. This is sodium benzoate is from sodium. The acid is here sodium. It's benzoic acid. The acid here is benzene sulfonic acid. Next question: water is formed during benzene sulfonation. Benzene sulfonation is basically B plus sulfuric acid gives us. So yeah, this is a correct statement. This is reversible answer, reversible reaction, and the this is the true state. Next question: the correct sequence of major chemical reactions involved in phenol production are. Is it the A option, B option, C option, or D option? So we go again stepwise. So we know the first step is sulfonation. So it is either A or D. So benzene plus I write HS here, just the abbreviation. This is not the formula for H2SO4. Please keep in mind, or I'll write H2SO4 itself. So it gives us sodium uh, benzene sulfonic acid. Okay. Then this benzene sulfonic acid reacts with sodium sulfite. This is sodium sulfite, N2SO3. So this is neutralization. It gives us sodium benzene sulfonate. So sodium benzene sulfonate then fuses with NaOH to give us sodium phenoxide. Then sodium phenoxide plus again H2SO4 gives us, here SO2 is also used, I guess, to give us crude phenol. And rest are the separation processes, but these are major chemical reactions. So sulfonation, then neutralization, then fusion, then acidification. So this is the correct answer here. Any doubts, anybody? Do you have any questions? So if there aren't any further questions, I'll go ahead and close this session for today. Thank you everybody for joining.